Hello, this video here is just a little addendum to the previous video for section 6.2, a few examples that I forgot to do, but we'll do them right here. Very important examples that I really want you to see that deals with our rules of exponents and also converting radicals to rational expressions. If we look at this, we have the fifth root of b squared divided by the 10th root of b cubed. Now this is where we have to be careful. Notice our indexes are different. And if we remember all the rules that we've applied up to this point, our indexes had to be the same. Well, first of all, let's write this as a rational exponent instead of a radical. Well, if we deal with the top first, where this is my denominator and this is my numerator, so it's 2/5, I can rewrite this as b to the 2/5 power. Here I can write this as b to the 3/10 power. And now if we think about it, well, hey, this is just some base b. They have the same base, and they're raised to some power. Well, I can use the quotient rule here. And if I do that, I can rewrite this as b to the 2/5 minus 3/10. Now, we recall in order to subtract fractions, they have to have a common denominator. Well, finding the common denominator when it's written like this is the same thing as finding the similar index so that we could do this operation. So 2/5 is 4/10, so I'm just going to write it here. B to the 4/10 minus 3/10 is b to the 1/10. And if we simplify that or write it as a radical, we have the 10th root of b to the first power, or the 10th root of b. So let's go back and review this just for a moment. Writing this as rational exponents, as we did here, is a great way to be able to change these indexes. Remember, the index is the denominator of our fractional exponent. So we can actually work with this when we convert it to this value and say, hey, we got to find a common index as the common denominator of these fractional exponents. All right, another important example that I want to take a look at is this right here. We have the quantity x to the 4th minus y to the 4th. And if we recall our rules of exponents, one thing that our exponents do not address is any sums or differences. There are no rules that are called the sums of powers or the differences of powers. There's no such thing. So here we have to be careful. Some people might think, hey, just distribute this to these powers. Well, that's called the product rule, or the power of a product rule, or the power rule, whichever one you apply, does not apply to addition or subtraction. So if you ever see a quantity like this, realize that the rules of exponents do not apply to sums or differences. If you see addition or subtraction, just pause for a moment and say, is there anything I can really do with this? Essentially, the only thing we can do with this is to rewrite it as a radical instead of a fractional exponent. It is the square root of x to the 4th minus y to the 4th. There is really nothing more we can do with this. Even if I factor it down, I'm not going to find any perfect square factors. And hopefully you remember how to factor these. Let's do it just for review. We'll review our factoring here. If I factor this, this is the difference of squares. So I can write it as x squared minus y squared times x squared plus y squared, still raised to the 1/2 power, because I didn't do anything with that other than factor it. And we see, oh, these aren't a perfect square because they have different signs. They're not the same thing being multiplied together. And I can factor this further to x plus y, x minus y, because this is still the difference of squares. And x squared plus y squared, because it's a sum of squares. There's no factoring that I can do in the real number system. And that's still raised to the 1/2 power. So I've broken it down as much as I can by using my ability to factor. And if we look at this, there are no perfect squares here. There is no repeated factor. So essentially, if I want to take the square root, there's nothing I can do with it here. I have no values times themselves, no perfect squares. So this is as far as I can really go. So watch out for those sums and differences. They can sometimes throw us for a little loop, but even if I expand it out, it's as far as I can go. It's the same thing as this, just in factored form. So I could write it as that and leave it. That's as far as it goes. All right. Now sometimes when it comes to our fractional exponents, our rational exponents, we can use our tools of factoring to maybe simplify this, or maybe do some math later on, some other operations we may have to do to something. We can use factoring to help simplify this. Now, if I look at this, I see this 3/2 as my exponent power here, and I can actually factor that out to simplify this a little bit. So I'm instructed to factor x to the 3/2 from this. And if we remember factoring, we're going to treat that as the greatest common factor. And to factor it out, we essentially need to subtract it. We're using the quotient rule. Factoring is just like dividing, breaking it into its parts. So if I do that, if I want to factor out x to the 3/2 from this quantity, what is it going to leave me with? Well, if I'm factoring it out, I'm subtracting 3/2 from this power, because that's my power. I'm dividing it out. So 5/2 minus 3/2 would be 2/2. Well, x to the 2/2 is x to the first power, which is just 1. And then this minus x to the 3/2, if I'm factoring out x to the 3/2, dividing out x to the 3/2, well, what's x to the 3/2 power divided by x to the 3/2 power? This is where our, let me write it over here, where our quotient rule and our zero exponent rule actually applies at the same time here. If I use my quotient rule, this power minus this power, the top minus the bottom, 3/2 minus 3/2 is 0. X to the 0 power is 1. Now you've been told that anything to the 0 power is 1. Well, this is why. Anything to 0 power is 1. Because our powers, top and bottom, are the same. Okay? Now, anything divided by itself is 1, and that's what the 0 power is telling us. So if I'm going to divide x to the 3/2 out of this right here, I'm going to get 1, because I'm dividing this by itself. 3/2 minus 3/2 is 0. Anything to the 0 power is 1, or anything divided by itself is 1. So notice this factor, we went from having two terms that had fractional exponents to here we turn it into a factor of x to the 3/2 times x minus 1. These two terms have no fractional exponents. They're one way to simplify it. So we can also use factoring when it comes to these rational exponents. Sorry about missing these examples in the previous video and extending that a little bit, but here you have it. Please keep practicing and keep watching. Thank you.